Module 16, Lecture A, Tree Modeling. By the end of this lecture, you will be able to fit decision tree classifiers and regressors for nonlinear prediction tasks, configure split criteria, depth, leaf size, and weighting controls, and visualize and interpret fitted tree rules and predictions. Tree estimators. Classification trees. A classification tree is a decision tree that predicts categories by splitting data into more uniform groups using input features. Each decision point applies a rule, and each branch leads toward a final class prediction. This approach is useful because it can capture complex patterns and feature interactions without requiring predefined assumptions. A classification tree builds a decision hierarchy by repeatedly splitting training data into groups that are more similar in class membership. These splits can use different types of predictors, such as patient age or lab results in medical screening, to assign cases to categories like risk levels. Because the process adapts to different regions of the data, classification trees are useful for capturing complex patterns based on conditional logic. A classification tree predicts a new observation by looking at the class distribution in the leaf it reaches, often giving both a class and an estimated probability. Its path through the tree makes the prediction easy to interpret. The tree must be balanced in depth because overly deep trees can overfit noise, while overly shallow trees may miss important patterns. This mix of accuracy and clarity makes classification trees useful in tasks such as fraud detection and customer segmentation. Python code, classification trees. Fit a classification tree to the iris data to learn how the flower classes are separated. The learned splits create nonlinear decision boundaries, which can be visualized as decision regions. Report the model's accuracy to summarize its classification performance. We import the main tools needed for a simple classification workflow: NumPy for numerical arrays, Matplotlib for visualizing data, and Scikit-Learn for building and evaluating the model. We also load the classic iris dataset, which contains flower measurements used to train and test classification algorithms. We import three key tools from Scikit-Learn: a train test split function to divide the data into training and testing sets, a decision tree classifier to build an interpretable classification model, and an accuracy score function to compare predictions with true labels. Together, these tools let us train the model and evaluate how well it performs on unseen data. We load the iris dataset from Scikit-Learn, a common dataset for flower classification. We then focus on the third and fourth measurements, petal length and petal width, because they are simple to plot and useful for visualizing decision boundaries. The iris data is prepared by using only the third and fourth flower measurements as input features, while the species labels are kept as the target. This simplified setup supports training a classification model and makes the results easier to visualize. The code first verifies that the iris dataset has the expected size: 150 samples, 2 selected features, and 150 target labels. If the data does not match these dimensions, it raises an error. This check helps ensure the data is loaded and formatted correctly before analysis continues. The dataset is split into training and testing sets using Scikit-Learn's train test split function, with 30% reserved for testing. Stratification keeps the class proportion similar in both sets, and a fixed random state makes the split reproducible across runs. We keep the decision tree simple by limiting its depth to 3, which reduces unnecessary complexity and makes the model easier to interpret. A fixed random state ensures the results can be reproduced. The tree is then trained on the data, learning the best splits to classify the iris species accurately. Use the trained decision tree to predict labels for the test data. Then compare those predictions with the true test labels. The resulting accuracy shows how well the model performs on unseen data and how effectively it generalizes. The output reports the Scikit-Learn version for reproducibility, then shows the decision tree's test accuracy to summarize performance on unseen data. It also gives the tree depth and number of leaves, which indicate how complex and interpretable the model is. To build a grid for showing predicted decision regions, set the range of the first features slightly beyond the data. Use the feature's minimum value -0.4 and its maximum value +0.4 to add padding around the edges. To set the vertical limits for the decision region plot, we use the second feature's range across the data. We subtract 0.4 from its minimum value and add 0.4 to its maximum value, creating a small buffer around the grid for clearer visualization. We use NumPy's mesh grid function to create a grid across the feature space. The grid is built from evenly spaced points between the minimum and maximum values in both dimensions. By predicting a class for each grid point, we can visualize the model's decision boundaries. To visualize decision boundaries, the x and y values from the mesh grid are combined into coordinate pairs and passed to the decision tree for prediction. The predicted classes are then reshaped back to the grid layout, making it possible to display how the model separates different regions. We create a plotting canvas with Matplotlib, then use a filled contour plot to show the decision tree's predicted classes across a grid of feature values. The semi-transparent color regions make it easier to see how the classifier divides the feature space into different decision areas. A scatter plot is created with Matplotlib to show the iris test data, using two selected features as the horizontal and vertical coordinates. Each point is colored by its true class label, with the Viridis color map, and black edges make the points easier to distinguish. The plot is titled Decision Tree Classification Regions to make its purpose clear. The horizontal and vertical axes are labeled with the first and second feature names, helping viewers understand what each axis represents and interpret the classification regions correctly. The code adds a legend to the plot, using the scatterplot's class labels from the iris dataset, so each color can be matched to a flower species. It then displays the completed visualization, including the decision regions and legend, so the results can be interpreted. This script trains a simple decision tree classifier on the iris dataset using two flower measurements. It splits the data into balanced training and test sets, limits the tree depth to keep the model interpretable, and reports its test accuracy along with the tree's size. It then visualizes the learned decision regions and overlays the test points, showing how the tree separates the flower classes with nonlinear boundaries. Regression trees.
Regression trees predict continuous values, such as prices or times,
by splitting data into groups based on features. Each final group gives a prediction using the average value of similar training examples. This makes the model easy to interpret and helps predictions reflect typical outcomes from past cases. Regression trees are useful for prediction tasks where relationships are nonlinear or depend on interactions between features. Instead of fitting one overall trend, they split the data into regions and build local rules for each region. This helps them capture patterns, such as changing effects of temperature, advertising, or vehicle mileage, that simpler linear models may miss. A regression tree makes stepwise predictions by giving every observation in a leaf the same value, so predictions change sharply at split points. This can work well when the data has natural segments, such as pricing bands or risk profiles. But if the tree grows too deep, it may overfit noise rather than capture general patterns. The goal is to balance predictive accuracy with clear interpretable rules. Python code, regression trees. Fit a regression tree to make numeric predictions, then explain how the learned leaf nodes produce stepwise prediction values. Finally, compare performance on the training and test data in a simple way to judge how well the model generalizes. This setup imports the main tools needed for a simple machine learning workflow. NumPy supports numerical work with arrays. Matplotlib helps create visualizations, and Scikit-Learn provides machine learning utilities. From Scikit-Learn, we use a train-test splitting tool to separate data, a decision tree regressor to build the model, and mean absolute error to measure prediction accuracy. We create a small, nonlinear regression dataset to model home prices. A fixed random seed makes the results reproducible, and home areas are generated from 40 to 220. Prices are based mainly on area, with an added increase for homes larger than 130, plus normally distributed noise to make the data more realistic. The area data is reshaped into a single column format, so Scikit-Learn can treat each value as one input example. The price data is then set as the target to predict, giving the regression model properly matched features and outputs. Before training a model, confirm that the feature data and target values have the same number of rows. This ensures every input has a matching target. If they do not match, raise an error to prevent unreliable training or predictions. The dataset is split into training and testing parts using Scikit-Learn's train-test-split function. 25% of the data is reserved for testing, so the model can be evaluated on data it has not seen before. A fixed random state of 42 makes the split reproducible, helping us reliably assess how well the model generalizes. We build a simple decision tree regressor by limiting its depth to 3 and requiring at least 6 samples in each leaf. These settings keep the model easier to interpret and help reduce overfitting. A fixed random state makes the results reproducible, and the tree is then trained to learn the relationship between home area and price. We evaluate the model by calculating mean absolute error on both the training and test data. The training error shows how close the model's predictions are on data it has already learned from, while the test error shows how well it performs on new, unseen data. Together, these scores help judge the model's accuracy and reliability. The output reports the Scikit-Learn version for reproducibility, then summarizes the decision tree's complexity using its depth and number of leaves. It also shows the mean absolute error on both the training and test data, rounded to 1 decimal place, to compare how well the model fits known data and performs on unseen data. The errors are given in thousands of dollars for clarity. A smooth range of input values is created and shaped so the trained decision tree regressor can make predictions across it. These predictions are then used to show how the tree models the relationship between the feature and the target. Because regression trees predict in steps, the result highlights their piecewise constant behavior. The visualization shows how a regression tree predicts home prices from home area. It plots the training homes as scatter points, then overlays the tree's predictions as a red stepwise line across a smooth range of areas. The axes label home area in square meters and price in $1,000, and a legend distinguishes the data from the prediction. This script uses a regression tree to predict housing prices from home area using synthetic data with a nonlinear pattern and added noise. It splits the data into training and test sets, trains a shallow decision tree regressor for interpretability, and evaluates accuracy with mean absolute error on both sets. It also reports basic model details, such as tree depth and number of leaves, then visualizes the tree's stepwise predictions against the data, to show how the model approximates the price relationship. Multi-output tree models. Multi-output tree models extend decision trees to predict several related targets at the same time. Instead of optimizing for one outcome, they choose splits that improve prediction across all targets, creating groups that are more consistent overall. This shared structure works well when the outcomes are connected, helping the model capture relationships efficiently. Multi-output classification predicts several categorical targets for each data point using one shared tree. This can make the model easier to interpret and can improve consistency when the targets are related. The trade-off is that each split must balance multiple goals, so a choice that helps one target may hurt another. If the targets are mostly unrelated, separate models may work better. Multi-output regression predicts several numeric targets at the same time, such as sale price and time on the market. In a decision tree, each leaf returns a set of predicted values based on the training examples that reach it. This can reveal nonlinear patterns where outcomes change together. But each target still needs separate evaluation, because good performance on one output does not guarantee good performance on the others. Python code. Multi-output tree models. This example shows a multi-output regression tree that predicts two related numeric targets at the same time. The results compare the true target pairs with the model's predicted pairs. We import key Python libraries for a regression workflow: NumPy for numerical arrays, Matplotlib for visualization, and Scikit-Learn for machine learning. From Scikit-Learn, we use a tool to split data into training and testing sets, a decision tree regressor to predict continuous values, and the R-squared score to evaluate how well predictions match the actual results. A fixed, random seed is set to make the results reproducible. Then, 160 evenly spaced values from 0 to 10 are created and reshaped into a single column array, so they can be used as one input feature for the model. A small amount of normally distributed random noise is generated and added to target values based on sine and cosine of the first feature column. This creates a two-output dataset with slightly noisy paired targets. The result is useful for training a model to predict both target values at the same time. The code first verifies that the target data has exactly two columns, meaning each sample provides two target values. This is required for multi-output regression, where the model predicts multiple outputs at once. If the target data does not match this structure, the code raises an error to prevent problems later. We split the dataset into training and testing parts using Scikit-Learn's train-test-split function. A quarter of the data is kept for testing, while the rest is used to train the model. Setting the random state to 42 makes the split reproducible, so results can be compared consistently on unseen data. We create a decision tree regressor to predict continuous target values. Its depth is limited to 4, and each leaf must contain at least 5 samples, which helps keep the model from becoming too complex and overfitting. A fixed random state makes the results reproducible. The model is then trained on the feature data and the two target values, so it can learn patterns for future predictions. The decision tree predicts values for the test data by applying its predict method to the test features. Each result contains 2 predicted target values. The model is then evaluated with the R-squared score for each target separately, showing how closely the predictions match the true values without combining the 2 scores. The output first checks the Scikit-Learn version to support reproducibility, then confirms the prediction array has the expected shape, with 2 targets per sample. It then reports separate R-squared scores for the sine and cosine targets, showing how closely the model's predictions match each set of true values. We create a scatter plot to compare the true sine and cosine target pairs from the test set with the pairs predicted by the decision tree model. Both sets of points are shown with partial transparency, making it easier to see how closely the predictions align with the actual values. The plot is titled to show it compares multi-output decision tree predictions. The x-axis represents sine target values, and the y-axis represents cosine target values. A legend separates the true data pairs from the model's predicted pairs, and the plot is displayed so the two can be visually compared. This example shows multi-output regression with a decision tree that predicts both sine and cosine values from one input feature. A noisy dataset is split into training and test data, and the model learns to predict the two targets at the same time. Its performance is measured with R-squared scores for each target, and a scatter plot compares true and predicted target pairs to show how closely the model captures their relationship. Split controls. Classification split criteria. In a decision tree, classification split criteria determine which question to ask at each node. The tree compares possible splits across features and chooses the one that makes the resulting groups more consistent in their class labels. This choice shapes the tree's structure by deciding which features appear earlier and which patterns the model emphasizes. Decision trees often choose splits using impurity measures such as Gini impurity or information gain. Gini favors splits that make nodes more dominated by one class, while information gain focuses on reducing uncertainty. These criteria often choose similar splits when the data pattern is clear, but they can differ in cases like isolating a small distinct group versus improving purity across more records. Knowing this helps explain why a tree selects one feature over another. Choose a classification split criterion based on your modeling goal, the classes involved, and the cost of different errors. Defaults may work for simple problems, but rare or important minority classes often require attention to class weights, tree depth, and whether a split will generalize beyond a few observations. Evaluate split choices as part of a broader strategy that includes validation, interpretability, fairness, and domain knowledge. Python code. Classification split criteria. This section compares split criteria in a classifier. Gini and entropy both measure how mixed the classes are, but they do so in slightly different ways. The printed results highlight how these choices can lead to practical differences in the model. We import key Scikit-Learn tools to build and evaluate a simple classification model. The Wine dataset loader provides sample data. The train test split function separates it into training and testing sets, and the decision tree classifier creates the model. Finally, the accuracy score function measures how well the model predicts unseen wine data. We load Scikit-Learn's built-in wine classification dataset, which includes measurements for different wines and their class labels. The feature data and labels are separated, so the dataset is ready for pre-processing and model training. Before training, the code verifies that the feature data and target labels have the same number of rows. This confirms that each set of features has a matching label. If they do not align, it raises an error so the issue can be fixed before model training or evaluation. The dataset is split into training and testing sets using Scikit-Learn's train test split function, with 30% reserved for testing. Stratified splitting keeps the class distribution consistent with the original data, supporting a fair evaluation. A fixed random state makes the split reproducible across runs. The setup compares decision tree models using two split quality measures, Gini and entropy. An empty results collection is prepared to store each model's performance, such as accuracy, so the two criteria can be evaluated side by side. The process compares decision tree classifiers using the Gini and entropy splitting criteria. For each one, a tree with a maximum depth of 3 is trained on the training data, used to predict the test labels, and evaluated by accuracy. The root feature and final tree depth are also recorded, so the two criteria can be compared later. The code reports the Scikit-Learn version to support reproducibility, then prints a labeled summary of decision tree results. For each tree, it shows the split criterion, rounded accuracy, root split feature, and tree depth. This makes it easy to compare how different criteria affect both performance and tree structure. This script compares decision tree classifiers that use Gini and entropy as split criteria on the wine dataset. It trains both models with the same maximum depth and evaluates them using accuracy on a test set with preserved class balance. The output reports the Scikit-Learn version, each model's accuracy, the feature chosen for the first split, and the final tree depth, showing how the split criterion can influence both decisions and performance. Regression split criteria. In a regression tree, the split criterion decides how to divide data with numeric target values. Instead of making class groups purer, it aims to create child nodes where target values are close to their average. This reduces prediction error within each node and helps the tree form useful partitions for making accurate predictions. Regression trees often split data by reducing squared error, which helps avoid large prediction mistakes. This is useful when big errors are costly, such as separating high and low electricity use. However, squared error can be strongly affected by outliers, like rare, very large insurance claims, so it is important to consider data quality and the cost of different errors when choosing this split criterion. In regression trees, using absolute error can make the model more robust when data includes outliers or is skewed. It helps the tree focus on typical patterns instead of being pulled toward extreme values. Choose absolute or squared error based on the model's goal, and tune it together with settings like tree depth and leaf size to reduce overfitting and improve generalization. Python code. Regression split criteria. Regression trees can choose splits using squared error or absolute error. Squared error is more sensitive to outliers, while absolute error often produces steadier predictions when extreme values are present. We begin by importing the main tools needed for the task: NumPy for numerical work and arrays, Matplotlib for visualization, and Scikit-Learn for machine learning. From Scikit-Learn, we use the decision tree regressor to build regression models. Together, these libraries support data handling, plotting, and model creation. We create a small nonlinear regression dataset with outliers. To make the results reproducible, we use a fixed random seed of 42, then generate 80 evenly spaced feature values from 0 to 10. We create a target variable with a smooth nonlinear pattern, then add random variation to make it more realistic. The pattern is based on 2 times the sign of the input values plus 0.4 times the input values. Finally, normally distributed noise with mean 0 and standard deviation 0.35 is added to each target value. We create artificial outliers by choosing 3 positions in the target array and increasing their values by 7. This produces unusually high target values in the dataset. The goal is to test how different regression tree split criteria respond to these outliers during training. Reshape the input values into a 2-dimensional format because Scikit-Learn requires features to be structured this way, even with only one feature. Then, confirm that the number of feature entries matches the number of target values. If they differ, raise an error, so each input has a corresponding target before training. We create a decision tree regressor in Scikit-Learn and set it to use squared error, so the tree chooses splits that reduce the squared difference between predicted and actual values. Because this can be affected by outliers, we limit the tree to a depth of 3 to reduce overfitting. A fixed random state makes the results reproducible, and fitting the model lets it learn patterns from the features and target values. We build a decision tree regressor in Scikit-Learn using absolute error as the splitting criterion. So the model focuses on reducing absolute prediction mistakes. Limiting the tree depth to 3 keeps the model simpler and helps reduce overfitting, while a fixed random state makes the results reproducible. After fitting the tree to the features and target values, it learns patterns in the data, including behavior influenced by outliers. A smooth set of input values from 0 to 10 is created and shaped for use with the regression trees. Both the squared error tree and the absolute error tree then predict across this same range. Comparing these predictions shows how each split criterion produces a different stepwise model of the data. We first check the Scikit-Learn version to support compatibility and reproducibility. Then, we compare the number of leaves in 2 decision trees, one using squared error and the other using absolute error. This shows how the split criterion affects tree complexity and sensitivity to outliers. The plot compares training data, outliers, and 2 regression tree prediction methods. The training points are shown in gray, while the outliers are emphasized in red. 2 prediction lines are then added, one for a regression tree using squared error, and another using absolute error, making it easy to compare how the criteria respond to outliers. The plot is finalized by adding a clear title about regression tree split criteria with outliers, labeling the feature values on the x-axis and the numeric target on the y-axis. A legend identifies the training data, outliers, and predictions from the 2 regression trees. The visualization is then displayed to show the results of the analysis. This script compares how regression trees behave with outliers when using squared error versus absolute error as the split criterion. It creates noisy nonlinear data with a few large outliers, then trains one tree with each criterion. Squared error is more sensitive to outliers and may produce more variable, complex predictions, while absolute error is less affected and can give steadier results. The output compares their prediction curves and reports the number of leaves to show how the criteria influence tree complexity. Depth and leaf controls. Depth and leaf controls limit how much a decision tree can grow and how much evidence it needs to create rules. These limits help prevent the tree from learning overly specific patterns that do not generalize well. If the tree is too shallow, it may miss important interactions, but if it is too deep, it may overfit by treating random noise as meaningful. Leaf size controls in decision trees require enough observations before a node can split or become a final leaf. This prevents predictions from relying on very small, unreliable groups, such as only a few similar cases. Larger leaf sizes create broader, more stable data segments, which improves trust in the predictions and makes the tree's rules easier to interpret. Decision tree depth and leaf size settings work together to control model complexity and generalization. Deeper trees can still be cautious if each leaf needs many observations, while smaller leaf sizes can create more detailed trees. The best balance depends on the amount of data, noise, and the model's purpose, with stricter limits often preferred when stable, explainable rules are important. Simpler trees are usually easier for stakeholders to understand. Python code, depth and leaf controls. Compare how tree depth and leaf size affect a decision tree. Tighter controls usually create simpler decision rules, while test accuracy reveals the trade-off between simplicity and generalization. We import key Python libraries for a simple classification experiment: NumPy for numerical work, Matplotlib for visualization, and Scikit-Learn for machine learning tools. Scikit-Learn provides a moon-shaped synthetic dataset, a way to split data into training and testing sets, and an accuracy measure to evaluate predictions. We also use a decision tree classifier to study how model settings affect complexity and performance. We create a small nonlinear classification dataset using the makeMoons function, which produces two interleaving half-circles. The dataset has 500 samples, with added noise to make the task more challenging. A fixed random state ensures the same data is generated each time the code runs. First, confirm that the generated feature data has the expected shape, 500 rows and 2 columns. If it does not, raise an error to stop the process. This ensures the data is correctly structured before any analysis or modeling begins. We split the dataset into training and testing sets using Scikit-Learn's train-test-split function, reserving 35% for testing. This lets us evaluate the model on unseen data and better judge how well it generalizes. The split is stratified to keep class proportions consistent, and a fixed random state makes the results reproducible. We define 3 decision tree classifier settings using tuples that specify maximum tree depth, minimum leaf size, and a label for identifying the configuration. These settings compare a shallow tree, a balanced tree, and a highly flexible tree with no depth limit. The depth controls how complex the tree can become, while the minimum leaf size helps reduce overfitting. The code first reports the Scikit-Learn version to support compatibility and reproducibility. It then prints a header for a results table that compares decision tree settings, such as depth, minimum leaf size, number of leaves, and training and test accuracy. This makes it easier to see how different configurations affect model performance. The process tests several decision tree configurations and records their performance. For each setting, a tree is trained on the training data. Then its accuracy is measured on both the training and test sets. The results include the setting label, tree size, measured by number of leaves, and the 2 accuracy scores. Each model summary is then printed with its depth, minimum leaf size, number of leaves, and accuracies rounded to 3 decimal places. We extract the descriptive labels and test accuracy scores from the results data. These 2 lists are then used to visualize how different tree control settings affect test performance. This code creates a bar chart to compare test accuracy across different tree control settings. It sets up a plot, draws bars using the provided labels, scores, and colors, then adds a title and axis labels for clarity. The y-axis is limited from 0 to 1, so the accuracy values are shown on the proper scale, and the plot is then displayed. This script shows how decision tree complexity affects performance on a noisy synthetic dataset. It compares a shallow tree, a moderately constrained tree, and a highly flexible tree, then reports training and test accuracy for each. The results illustrate the trade-off between fitting the training data and generalizing to new data. Simpler trees may perform better on the test set, while very flexible trees can overfit. A bar chart summarizes the test accuracy across the settings. Tree interpretation. Class weight effects. Class weights change how a decision tree treats different outcomes, giving more influence to classes that are rare or more important. This can shift both the splits the tree chooses and the predictions it makes, especially in imbalanced data. As a result, the tree's rules reflect the weighted priorities. not only the most common patterns in the data. Class weighting in decision trees changes how leaf predictions are chosen by giving some classes more importance than their raw counts suggest. A less common class can be predicted if its weight is high enough, such as fraud being prioritized over legitimate transactions, or high-value churn cases receiving more attention. As a result, the tree's decisions reflect both the data patterns and the priorities set through class weights. Class weights can make a decision tree look more complex by adding splits that emphasize minority or high-priority cases, instead of letting the majority class dominate. This can improve important outcomes, such as detecting severe public safety risks, but it may also increase false positives or make predictions more aggressive for the weighted class. To interpret a weighted tree, focus on its visible rules, predicted classes, and the real-world impact of prioritizing some errors over others. Python code. Class, weight, effects. Weighted and unweighted decision trees can make different predictions because class weights influence how leaves choose their final class. As a result, adding weights can shift the decision regions, compared with an unweighted tree. This setup imports the main tools needed for a simple classification workflow. NumPy supports numerical work with arrays, Matplotlib creates plots, and Scikit-Learn provides machine learning utilities. The code also checks the Scikit-Learn version, generates a synthetic classification dataset, and imports a decision tree classifier for building a classification model. We create a small, imbalanced classification dataset using Scikit-Learn's make classification function. It has 300 samples, 2 informative features, and a 90-to-10 class split. The class separation is set to control how distinct the groups are, and a fixed random state makes the dataset reproducible. Before modeling, the code confirms that the dataset has the expected structure: 300 samples, 2 feature columns, and 300 labels. If the data does not match these dimensions, it raises an error. This early validation helps prevent problems later in the modeling process. We create 2 decision tree classifiers to compare how class weighting affects training. The first tree treats all classes equally, with a limited depth and a fixed random state for reproducibility. The second tree is similar, but gives the minority class much higher weight, so the model pays more attention to it when making splits. An unweighted decision tree learns from the dataset without accounting for class imbalance. A weighted decision tree uses the same data but gives more importance to the minority class, helping the model pay closer attention to that less frequent class and potentially predict it more accurately. To compare the unweighted and weighted decision trees, we measure how often each model predicts the minority class. For each tree, we generate predictions from the features and take the average of those predictions to get the minority class prediction rate. Comparing these rates shows how class weighting changes the model's behavior. The output first reports the Scikit-Learn version to support reproducibility. It then compares the true minority class rate in the data with the rates predicted by an unweighted decision tree and a weighted decision tree. This shows how adding class weights changes the model's tendency to predict the minority class. To visualize the weighted decision tree's decision regions, we define a grid that covers the full feature space. For each of the 2 features, we take the minimum and maximum values and extend the range slightly by half a unit on both ends. This ensures the grid reaches beyond the data points, making it easier to see how the tree classifies different areas. To visualize decision regions, we create evenly spaced X and Y values across their full ranges, then use them to form a coordinate grid. These grid coordinates are combined into a single set of points, so the decision tree model can make predictions across the entire area. A weighted decision tree predicts class labels across a grid of points covering the feature space. These predictions are shaped for plotting, so the decision boundaries can be visualized, showing how class weighting changes the model's decision regions. A new plotting area is created. Then filled contours show the weighted decision tree's decision regions using a cool-warm color scale with partial transparency. The actual data points are plotted on top, with their positions based on the two features and their colors based on class labels. Black outlines and a moderate point size make the samples easier to see against the background. The plot is formatted to show how a weighted decision tree gives more influence to the minority class. The axes are labeled for the two features, and a class legend is placed clearly in the upper right. Displaying the plot lets us compare the decision regions and see the effect of class weighting. This script shows how class weighting changes decision tree behavior on an imbalanced synthetic dataset. It trains one tree normally and another with extra weight on the minority class, then compares their predictions. The weighted tree predicts the minority class more often, and its decision boundaries shift to give that class more influence. Handling missing values. Missing values matter in decision trees because each prediction follows a path of feature-based decisions, and a missing feature can interrupt that path. Models may handle this by filling in missing values before training, or by learning during training how to route missing cases, such as choosing a branch or using alternative features. For interpretation, it is important to know whether missing data was handled before modeling or built into the tree's decision process. Missing values in decision trees should be interpreted in terms of what they may mean in the real world, not just how they route a case through the tree. A missing value might reflect a data error, a delayed measurement, or a meaningful condition, and each possibility can affect predictions differently. This matters especially when missing values appear near the top of the tree, because they can influence many later decisions. Analysts should check whether missingness is rare, tied to certain groups, or related to the outcome being predicted. When explaining a decision tree, always clarify how missing values were handled. If missing data was filled in before training, describe the replacement method and how it may affect the learned rules. If the model handles missing values directly, explain whether it uses default paths, learned patterns, or alternative decisions. This transparency helps prevent misinterpretation and supports more reliable predictions when data is incomplete. Python code: handling missing values. This example shows that missing value handling can affect how a decision tree is interpreted. Different imputation choices may lead to different paths through the tree, producing different explanations for the same case. We import key Python libraries for our machine learning workflow: NumPy and Pandas for numerical data and data frames, and Scikit-Learn for modeling tools. From Scikit-Learn, we use a simple imputer to fill missing values and a decision tree classifier to build a classification model. Together, these imports prepare the environment for data handling, missing value treatment, and decision tree training. We create a small Pandas dataset to keep the decision tree simple and easy to interpret. It includes income and debt values, both measured in thousands, with income increasing and debt decreasing across the examples. This simple structure makes it easier to see how different imputation strategies change the tree's behavior. We define a target array that labels each loan applicant as either high risk or lower risk, using 1 for high risk and 0 for lower risk. Then we create a new applicant record with missing income and a debt value of 24. This example is used to test how different ways of filling in missing income affect the decision tree's risk prediction. Before modeling, The code verifies that the loan dataset has the expected size, 8 rows and 2 columns. If the data does not match this format, it raises an error. This early check helps catch unexpected data issues before fitting models or making predictions. We handle missing loan data by using a Scikit-Learn imputer that fills each column's missing values with its median. After transforming the data, we train a decision tree classifier with a maximum depth of 2 and a fixed random state for reproducibility. The model is then fit to the cleaned loan data using the risk labels as the target. Missing values in the loan data are first replaced with 0 using a simple imputation approach. The clean data is then used to train a decision tree classifier with a maximum depth of 2 and a fixed random state for reproducible results. This lets the model learn patterns between the imputed loan features and the risk labels. The describe path function explains how a decision tree reaches a prediction for a specific row. It finds the sequence of tree nodes the row passes through, then prepares a set of plain language rules for those decisions. This creates a readable summary of the tree's decision process. The loop checks each node in the tree's decision path and looks up its feature identifier. A negative identifier means the node is a leaf, so it is skipped. This way, only decision nodes with valid features are used when generating rules. At each decision tree node, the code identifies which feature is being tested, retrieves the node's threshold, and gets the applicant's actual value for that feature. It then compares the value with the threshold to decide whether to move left or right in the tree. The code chooses which branch of a decision tree to follow by comparing the current feature value with a threshold. If the value is less than or equal to the threshold, the path goes left. Otherwise, it goes right. It then records a short rule describing the feature, its value, the chosen direction, and the threshold, adding it to the list that represents the full decision path. The function combines the stored decision rules into one readable string, separating each rule with a vertical bar. This summarizes the decision path a tree followed for a specific input row, making the sequence of choices easier to understand. The new applicant's data is prepared in 2 ways. Missing values are filled using the training data median, and separately using a constant value of 0. Each version is then passed to its matching decision tree model to predict the applicant's risk. Comparing the 2 predictions shows how the choice of imputation method can influence model results. The code checks the Scikit-Learn version, then evaluates a new applicant whose income is missing and debt is 24. It compares risk predictions from 2 models that handle the missing income differently, one using median imputation and one using constant imputation. For each model, it also reports the decision path, showing how the chosen imputation strategy changes the tree's reasoning and explanation. This script shows that the way missing values are filled in can change both a decision tree's prediction and its explanation. Using a small loan risk dataset, it compares median imputation with constant imputation for a new applicant's missing income. Each imputed version leads to a different decision tree path and can produce a different risk prediction. The main point is that missing value handling can directly affect model outcomes and how those outcomes are interpreted. Visualizing tree structure. A decision tree visualization turns a model into an easy-to-follow decision map. Each internal node asks a question about a feature, each branch shows an answer, and each leaf gives the final prediction. For classification, the leaf gives a class, while for regression, it gives a number. By following the path of conditions, you can see how the model reaches its result without relying on complex math. To interpret a decision tree, look at how the tree splits the data and what each node represents. The root node makes the first broad division, and lower nodes apply more specific conditions to form smaller groups. In a churn example, splits such as contract length, complaints, and monthly charges can identify customers likely to leave. A node's depth shows how many decisions led there, while its number of observations suggests how reliable that pattern may be. A tree visualization helps judge whether a model is understandable, believable, and useful for decisions. Shallow trees are often easier to explain because they reveal a few key patterns, while large trees may need simplification or focus on the most important branches. Checking whether the splits make real-world sense can also reveal possible data problems. So the visualization supports both interpretation and model validation. Python code. Visualizing tree structure. A small fitted decision tree can be understood by reading each node as a question. To make a prediction, start at the root and follow the answers down the tree until you reach a leaf. We import the main tools needed to build and view a decision tree model. Matplotlib is used for visualization, while Scikit-Learn provides the iris dataset, the decision tree classifier, and a tool for plotting the trained tree structure. We load the iris dataset from Scikit-Learn and use it for a simple classification task. To keep the decision tree model easy to interpret, we focus only on petal length and petal width as the input features, while the flower species serves as the target to predict. Validate the dataset by checking that the feature data and labels have the same number of rows, so every data point has a label. Also confirm that the feature data contains exactly 2 columns, matching the expected 2 features. If either check fails, raise an error to prevent inconsistent data from causing problems later. We create a decision tree classifier in Scikit-Learn with a maximum depth of 3, keeping the model simple and easy to interpret. A fixed random state makes the results reproducible. The classifier is then trained on iris flower measurements, learning rules from petal length and width to predict the iris species. A single flower is selected from the dataset, using its petal measurements as the input. The decision tree then predicts the flower's class and stores that result as the predicted label. This shows how the model classifies one specific sample based on petal length and width. The output first shows the Scikit-Learn version to support reproducibility. It then reports the sample flower's petal length and width, rounded for readability, and gives the predicted iris species. Together, these values connect the flower's measured features to the decision tree's classification. To visualize the fitted decision tree, we first prepare a Matplotlib canvas with a suitable figure size. Then, we use Scikit-Learn's plot tree function to draw the model, labeling the inputs as petal length and petal width, and using the iris species as class names. Filled colors and rounded nodes make the tree easier to read, and the plot is placed on the prepared axes. The code adds a clear title and axis labels to a decision tree plot for iris petal measurements. The labels explain that left branches represent true conditions, right branches represent false conditions, and deeper levels show more specific rules. It then displays the plot, so the decision tree can be visually explored. This script trains a simple decision tree on the iris dataset, using petal length and petal width to predict species. It limits the tree depth to keep the rules easy to interpret, then tests one sample and reports its measurements and predicted class. The main result is a color-coded tree visualization that shows how the classifier moved from measurement-based decisions to a final species prediction. In this lecture, you learned to fit decision tree classifiers and regressors for nonlinear prediction tasks, configure split criteria, depth, leaf size, and weighting controls, and visualize and interpret fitted tree rules and predictions. In the next lecture, Lecture B, we will go over tree regularization.
Thank you for your attention. See you all in the next lecture.